Hi, my name is Lin. I come from chemical engineering. Today my presentation name is electrocatalytic water splitting. The world's development of new energy is imminent. The reason is the energy sources such as petroleum, natural gas, coal, and petroleum gas belong to non-renewable resources. The Earth's stock is limited, and human survival is inseparable from energy, so it is necessary to find new energy. And with the increasing consumption of fossil fuels, their reserves are decreasing day by day, and one day these resources and energy will be exhausted, so it is urgent to find a new energy source with abundant reserves that doesn't rely on fossil fuels. Hydrogen is just such a secondary energy source. Hydrogen is at the top of the periodic table and has an atomic number of 1. It is a gas at room temperature and pressure, and a liquid at ultra-low temperature and high pressure. Molecule hydrogen emerges as a promising energy source due to its high energy density, small molecular mass, and no pollution, has received more and more attention in recent decades. As an ideal new energy source, it has the following features, such as lightweight, best thermal conductivity, abundant reserves, good combustion performance, environmental protection, convenient transportation, and so on. It can also be used as raw material, fuel, raw gas, and so on. And for example, as raw material, it can be used to do some catalytic hydrogenation, nitrogen reduction, and other reactions. As fuel, it can be used for fuel cell car. And electrocatalytic water splitting is a key process in renewable energy conversion. Primarily for hydrogen production, it involves the electrochemical splitting of water into hydrogen and oxygen gases by applying an external electric current. The product hydrogen gas can be used as a clean fuel, while the oxygen is released as a byproduct. This process is considered a promising pathway for hydrogen production, as water is abundant and the energy required for electrolysis can come from renewable sources such as solar, wind, and hydropower. And compared with other methods, electrocatalysis has low energy consumption, no radiation, and no pollution. It can also produce high purity products. And water splitting has been extensively studied for energy storage and fuel production in a carbon neutral manner. Electrocatalytic water splitting can be performed in alkaline, neutral, or acidic media, each requiring different electrocatalysts, and is divided into two half reactions, the hydrogen evolution reaction and the oxygen evolution reaction. And electrocatalytic water splitting involves two half reactions, the HER, the reduction of water to hydrogen, and the OER, the oxidation of water to oxygen. And the water splitting process generally follows these basic steps. At the cathode, HER, water molecules are reduced and resulting in the production of hydrogen gas, and at anode, OER, water molecules are oxidized, leading to the formation of oxygen gas. And both reactions are catalyzed by specific materials known as electrocatalysts. The efficiency of water splitting depends on the ability of the electrocatalyst to lower the energy barrier associated with each half reaction. And for the mechanism of the different HER and OER, the HER, the hydrogen evolution reaction takes place at the cathode during water splitting, where electrons are supplied from an external circuit to reduce protons or water molecule into hydrogen gas. And the HER can be described by the following elementary steps. Proton absorption is hydrogen or the hydrogen ions absorbed onto the surface of the catalyst, and electron transfer in these steps absorbed protons gain electrons to form hydrogen gas, and the HER is typically facilitated by catalysts with high electrical conductivity and low hydrogen binding energies. Common HER electrocatalysts include platinum, palladium, and other materials like nickel, molybdenum, and these respective alloy or composites. And the key factors that influence the HER include the catalyst material. The catalyst should provide low overpotential for proton reduction, and for the surface area, the high surface area materials promote higher rates of HER. And stability. The electrocatalyst must maintain long-term stability in harsh electrolytic environments. And the next is about the oxygen evolution reaction. The oxygen evolution reaction takes place at the anode, where water molecules are oxidized to produce oxygen gas. The reaction is more complex compared to HER and involves the transfer of multiple electrons and protons. The OER typically follows a 4-electron mechanism, though a 2-electron pathway is also possible in some cases. And the key steps involved in the OER are water absorption. Water molecules are absorbed on the surface of a catalyst. Then is oxygen atom formation. The absorbed water molecules are oxidized, releasing protons and electrons. And then next is the oxygen bond formation. The oxygen atoms combine to form an oxygen bond, which results in the release of oxygen gas. Because OER is a multi-electron transfer process, it is generally more challenging and energy intensive compared to HER. And this requires electrocatalysts with high activity and stability at high overpotentials. Common OER electrocatalysts include iridium oxide, ruthenium oxide, and cobalt-based catalysts, which exhibit excellent catalytic activity, but still suffer from high cost and limited availability. And key factors that influence OER include the catalyst material. High performance electrocatalysts for OER often include noble metals or transition metal oxides, hydroxides, and spinels. And next is electrolyte conditions. The electrolyte pH and the concentration of ions can affect the efficiency of the OER. And last is the overpotentials. OER typically requires a higher overpotential than HER due to the complexity of the multi-electron process and bond breaking. And then the last is about the challenges and opportunities. And first is about the efficiency. Both HER and OER require significant reduction in overpotentials for practical application. The high overpotentials increases the energy required for the water splitting process and reduce overall efficiency. And then is the catalyst development. Identifying new and cost-effective catalysts with high activity and stability is a major area of research. Currently, noble metals like platinum and iridium are highly effective but too expensive for large-scale applications. And then is the stability. Over time, electrocatalysts may degrade, particularly during the OER, which is highly corrosive. Improving the long-term stability of these catalysts is essential for the viability of water-splitting technology. And lastly is about the integration with renewable energy. To ensure a sustainable and low-carbon process, electrocatalytic water splitting needs to be integrated with renewable energy sources such as solar or wind power to provide the electricity needed for electrolysis. And in summary, electrocatalytic water splitting offers a promising route to generate hydrogen fuel in an environmentally friendly manner. However, it faces challenges in terms of efficiency, catalyst development, and scalability. Significant ongoing research aims to reduce energy losses, improve catalyst stability, and makes the process more cost-effective for large-scale hydrogen production. And that's all. Thank you.